I'm going to introduce Ira Cohen, the speaker today. He received his Ph.D. from the University of Urbana Champaign. He's been the chief data scientist at HP Software. He's a specialist in time series forecasting and anomaly detection. And he's now the chief data scientist at Anodot. So here's Ira to speak about machine learning monitoring.
Hi, thank you very much, and I'm excited to be here at the conference. It's been the easiest conference to go to so far ever, actually. But I wish I could see everybody's faces and be there in person. And hopefully next year we can do some of the conferences in person. I wanted to talk today about scalable monitoring of machine learning models in production. And in particular, how do you use machine learning to monitor your machine learning models in production? So just as a background, everybody here knows about how machine learning evolved over the years and became from just publishing papers at MIPS and ICML to be something that's being used extensively in industry. And, you know, if you ask yourself, have you used machine learning today in your daily life? I'm sure the answer is yes. Any browsing, any call for Siri, anything for Google Home, all of that involves machine learning, as we all know. And if we look at the different products that use machine learning today, it's becoming more and more pervasive throughout various industries. So it started with a lot of ad serving and bidding, stock exchange and assistance, and now moving to self-driving cars and email and typing emails, autonomous analytics, transcription, product recommendation, fraud detection, churn prediction, writing an article, composing music, fake videos of actors that are not them really. So it's really going more and more and more deeply into all industries and becoming commonplace in a lot of products. So how do you actually develop machine learning as a capability into a product? So I like to think about it as a 5-step process. And the first step is defining what you want to solve and deciding whether you want to solve it with machine learning at all, and whether it's a good fit for machine learning to solve a particular problem with machine learning. Once you defined it, you want to start collecting. You're starting the research process. So this is step 2 and 3. You're collecting data, preparing data, then training and testing models, iterating on that, going back actually to step 2, collecting and preparing data. Sometimes you go back to step 1 and redefine the problem because you realize it had some limitation. But all of this step 1 to 3, keep iterating in the lab, if you will. And once there is a good understanding that the solution is valid, you start coding it so you can deploy it to production. You make it production ready, and now you deploy it, and now your models, whether it's a classifier of images, audio, churn predictor, whatever it is, ad bidding algorithm, whatever it is, it's now deployed into production and it's starting to do stuff. It's actually starting to function in reality. So the 5th step is tracking and monitoring what's happening in production. And usually that step could lead to refinement of the models, refining of the data, and basically it's a loop that continues on and on and on. Now, this 5th step, I guess it's been largely overlooked in the past few years. It's starting to be looked at more carefully as more and more capabilities and groups actually deploy their models into production. But it's still overlooked in terms of the capabilities around it and the maturity of teams to actually monitor their own models in production. So what can go wrong in production? And I posted a video just before the talk. Anybody who wants to go look while I'm speaking at this funny video about how South Park trolled Amazon Echo in one of their episodes a few years ago. Basically what they did, Cartman kept calling his Alexa, and anybody who had Alexa in the room with a TV would also react to it and perform the actions that Cartman meant. And people reported various things that went into their shopping carts based on this episode. And they never said it. It was the TV that said it, but it still went into their shopping cart, which arguably is not the right action for the product to do. There are costly, this was a funny mistake, but there are costly mistakes that also happened. This happened at the end of 2018. Google had a multi-million-dollar glitch where it flooded the internet with this yellow ad because of a problem with their ad bidding software. And again, the machine learning was functioning. It was functioning based on the parameters it was given, but it basically cost some speculate around $10 million for just 2 hours of a glitch. We all know about various biases that machine learning can have when it's trained on various types of data, or it might not be, maybe it was trained on good data, but then reality is different than what it was trained on. So it can be conceived as racist or sexist because of the way it's learned. And there are many, many things that happen. So if I want to summarize what type of problems could happen, the most common one that causes machine learning models in production to go haywire is problem with input features. So usually the input features will determine the outcome, and if there is a flaw in the mechanism that generates the input features for the models in production, it could be for a lot of various reasons in the pipeline that generates them. You would get garbage in and then garbage out, and your models may do the completely opposite thing of what they were supposed to do, and then this could end up losing money, just like in the Google case. Vulnerability. So the Amazon Alexa thing highlights the vulnerability that the designers did not think about, not understanding the context. So, if you will, dumb AI. So the Alexas were functioning perfectly in terms of speech understanding and even understanding the action to take and what to put in the shopping cart. But no human would have done this because it would have understood the context that these are products that are unreasonable, or this is not the voice of the person that usually gives the orders to Alexa. The third most common thing, or maybe it's the second after vulnerability, before vulnerability, is concept drifts and new untrained concepts appearing, or the concepts that were trained on changed. And this, for example, if you design a churn prediction model for games, it could be that the game mechanics have changed, and what constituted churn before, or the things that would help you understand churn before, actually drifted, and you need to retrain your models. Your models are stale. Then you have bias training sets. You have misclassifications. There could be a lot of reasons and a lot of things that could go wrong. Now, let me give you some concrete examples that cost companies that I know of a lot of money. For example, there was a company that had a churn analysis for a B2C company, and some input features that went missing in the pipeline, and then the default values are put in instead, basically caused that churn predictor to make a lot of errors, and the company was investing money in trying to keep customers that were not going to churn, while not investing in the customers that were about to churn. And that cost them quite a significant amount of money. It increased their churn overall. An ad tech company actually burned $300,000 of a budget in 10 hours because of an incorrect configuration of a bidding algorithm. So it was a runaway bidding algorithm. Again, the model itself was trained properly. It's just that the input features or the configuration of it was configured wrongly by somebody with that particular campaign. And that instance of the model basically outbid everybody and burned this budget, which was meant to last for about three months. And e-commerce had released a new recommendation engine that had a bug. And after a few months, they realized that they have a decrease in purchases, and they realized it was because the recommendation engine was not converting as it did before. Increased in block payments because of suspected fraud. So a lot of payment companies use fraud detection algorithms and models. And this was a case where there was a change in some of the bank IDs that were part of the features that would decide whether to block a payment transaction. And the models were not aware of it. And again, it caused flagging of fraudulent transactions as fraud when they were not. And of course, that leads to less payments being done and also frustration by the customers. So lots of things can happen. So what's the solution? The solution is to actually monitor your models, and this is not monitoring their response time or monitoring if they're producing errors from a software perspective, or this is not the monitoring that their server is up and running that's running the models. It's really monitoring the models themselves. That's something you can't expect from your DevOps teams to do. That's something that only the data science team can understand. And then once you monitor it, you need to track it for any unexpected changes in its outputs. So really it's about looking at what are the algorithms, what are the models I'm deploying to production. It's a classifier, it's a regression, and then define what should be the performance metrics for that. Then starting to collect these metrics continuously in production. Usually you would have a lot of instances of a model or a lot of actions that it will take, let's say a classifier classifying images. You want to aggregate that into some sort of metrics that will tell you how this classifier is performing over all the data that it sees in production while it's running. And then if you see that there are unexpected changes in these metrics, that should trigger that something might be going wrong and you should go and take a look at it. So to make it more concrete, if we're looking at a classifier or a regression, anything that has an input features and output features, and it doesn't really matter what type of model you're using underneath, whether it's a simple classical machine learning model like SVM or XGBoost, or it's or decision tree, or it's a deep learning deep network, doesn't really matter. If you the 2 points that are most critical to understand most of the problems are the things related to the input features and also tracking the output and then creating metrics out of this. So what does it mean to create metrics out of this? So if you think about a classifier, it keeps, if it's running in production, let's say it's supposed to classify images to digits, and I'll show this example later. It constantly gets new images and it classifies the image to the digits inside. So there's a constant stream of images flowing in and constant outputs coming out of that model in production. Now, you don't necessarily want to look at each individual decisions that classifier makes, but you rather want to look at various distributions of its output and inputs. So if we're talking about input features, if they are discrete valued, you want to start creating histograms of what were the input features that came in, the histogram of that. That should have some sort of steady behavior to it. If it's real valued features, you want to look at various statistics, and you could use the mean over some of the input features that came in, standard deviation, IQR, counts, percentile, and you could think about a lot of different distributions. Each one would be able to detect, from there you can detect significant changes to the input feature distribution. In terms of the output, well, you want to at least first look at, if it's a classifier, look at the distribution of the predicted classes. So usually in production, you won't have the actual label of the input, because if you had that, you would need the classifier in the first place. So, but if you look at the distribution of the predicted classes, it actually should more or less be stable if the input coming in is also randomly distributed from all the possible inputs that there are. you want to look at what we found also is very useful is looking at the confidence, the probability of the winning class. So how confident the classifier was at the winning class. Because what we found is usually that should be steady for each class. And then if you have output labels that are available, and in some cases you might be able to obtain the true label after a while, you want to also collect something around the confusion metrics, because that will tell you that whether your classifier is really degrading or not. The confusion metrics is definitely available when you're doing training and the testing phases of your models. It's not always available in production itself. But you can gain a lot of insights from looking at the other two, the distribution of predicted classes and the confidence of the winning classes. So we actually designed an open source that can do exactly this. Basically, it provides you with hooks both at the input and the output, and it could track a lot of different instances or a lot of different algorithms that are running in production. It's a client-server architecture, and basically it starts collecting the inputs and the outputs for every one of the models, and you can determine what is the buffer size. So how many samples do I need to see before I aggregate it into a number or a distribution? And then that gets collected over time, and then you can go and look at these time series basically of both the input distribution, the predicted values, and if you have the accuracies, you can also look at the accuracies over time and start to track the changes that happen. This is how kind of the code that you need to wrap it around your code. This is a Python code, so it's really one line of code. You put the hook inside, you wrap the agent around your predicted probability if it's a classifier, or if it's a regression, the predicted output, and it starts creating those metrics for you and storing them into CSV, and those could be uploaded to any system that supports visualization. So basically, you would start seeing both the feature distribution over time. You might see also the output probability over time, or the winning class probability over time, and you can plot it in your favorite dashboarding system, be it whatever that is, and then if you observe it enough, you can detect that there are significant changes and go find out what happened to your models in production. What's the problem with that? This is good if you have few models in production, and even if you have one type of algorithm like a churn predictor or an ad bidding algorithm that you deployed in production, usually there will be a lot of instances of the same model out there, each one maybe with a slightly different configuration designed for what the problem it's trying to solve. And in some cases, you might have millions of deployed models in production. And I can tell you, we have hundreds of millions of deployed models running constantly in memory in production because they're analyzing a lot of different pieces of information. So how do you actually scale, looking at things, dashboarding, to actually be alerted on any change that you should pay attention to without having to stare at dashboards all day long, because that doesn't scale. So the solution is actually, or at least one solution that we found very useful, is to use anomaly detection or time series anomaly detection on those metrics that you're collecting, both at the input features and the output features. So this is an example of an alert for a classifier. And it's basically showing me the max prediction probability of the classes. And as you can see from the chart here, it's quite steady. It's quite, it usually produces high confidence. It has high confidence in the predicted class, whatever the class is for this classifier. And all of a sudden, the anomaly is that it started having lower confidence than the normal. That should trigger, why did this happen? Maybe it's valid, maybe something in the input is really became fuzzy, but maybe there's a problem with the input features. And usually what we found when this is steady and all of a sudden it changes significantly, it's usually a problem in the input feature distribution. But now if you have a lot of models running in production, maybe if you looked only at this graph, you could have seen it, but if you get alerted on it and it's model 3,245 out of your 10,000 models running, you will never be able to pick this up manually. So you want something to alert you on that. So let me give you an example of how this works, or kind of things that go wrong, and how this looks like on a made-up example based on the digit recognition sample. I'll later show a real example, a real-life example of from our production environment that happened just a few days ago. So let's assume my problem is to produce a digit classifier, and I'm training basically a classifier that can identify 0 to 9 digits. This experiment is based on the MNIST data set, so it's a very widely used data set. The input features are basically floats or doubles, so they're not discrete valued. There are 28 by 28 pixels in every image, so that's the number of features that we have. And the output is one of 10 classes. And our classifier, we trained a neural network, but it really doesn't matter what you use as a classifier. 3 layers, it had about 200,000 parameters to train, but it was a very accurate classifier on this problem. Now, on the training set, the expected accuracy in production, we got 96.875%, and it also had a very high and stable confidence in the digit prediction. So whenever it said it's digit 5 or digit 2 or digit 1, it was quite confident about it. And that's and that you can see on the left. That's a chart you see on the left. And by the way, the shaded area is the confidence interval that our system learned for the output probability, confidence in output probability of each class. Now let's do something to make it wrong. So we took the test data, or the data that you would think you would see in production, and we basically just translated the pixels down in each image by a few pixels. I think it was 2 or 3 pixels down. Now, when we trained the classifier, we did not make it translation invariant. Of course, we could have done that, but we didn't, which could happen. And it could happen that all your images that are coming into this classifier somehow get a little bit translated down. Very, very plausible problem that could happen. What happened here? Basically, you can see a few examples with their prediction probability. It was making more mistakes, but it was also predicting with much lower probability the class that it thought it was. First of all, the accuracy went down to 18% on a test set, but we cannot measure this accuracy in production. Now, how does it look like? And this is the alert that you saw before. Basically, if before the output prediction probability was very steady at around 0.95, it all of a sudden dropped to around 0.7, and this is the alert that you get. And when you want, usually when you get an alert on the output prediction probability, not the distribution of classes, then you want to investigate first to see whether some of the input features changed. And in this case, in this graph here, what you see is this is the input feature distribution for all the different pixels. And you see that for a number of the pixels, this distribution completely changed because of this translation. Which helps you understand that something in the input really changed dramatically, which explains why this drop happened. And you go and investigate it and understand what happened, why it happened, and fix it. Whether it, a hot fix for this kind of case would be to first make sure that the translation doesn't happen, and then I would go back to the lab and retrain my models so they are translation invariant. So this is an example from a made-up example, but this kind of things happen all the time. I wanted to show you a real example from our own system. So we have an anomaly detection system or business monitoring system that takes in hundreds of millions of time series not related to data science, but rather revenues and conversions and purchases and cloud costs and various things that the companies using us actually want to monitor. And we apply our machine learning algorithms, in particular anomaly detection algorithms, to it, and we detect anomalies and alert on them. Now we need to monitor our models in production, and because we have models for every single time series that flows in, we have hundreds of millions of models running in parallel in production, each one maybe applying the same type of algorithm on the time series, but each one has its own modification to it. And we need to know that they are running okay and nothing wrong is happening with them. The system might be up and running, but if our algorithms start becoming bad, then our clients would experience a lot of alerts and false positives that tell them revenue is down when it's not down, or things of that sort. So we have to make sure our algorithms are constantly running. This is an alert that we got a few days ago. This is from, I think, June 8th. It basically told us that so every anomaly that we find, we have a classifier that decides what is the score of this anomaly. You can think of it as a classifier or a regression. It basically gives a number between 0 and 100, which is bucketed in buckets of 10. So it's we implemented it as a classifier, and what we collect in our environment is metrics that say, what is the percentage of each score of each basically output from 90 to 100, from 80 to 90, 70 to 80, and so on. What is the distribution of those scores for all the anomalies that we find? If there is a significant change, we want to be alerted on that. So on June 8th, there was a significant change, and all of a sudden, the percentage of anomalies that had the very highest score, the end bucket from 90 to 100, actually spiked from around 4.6% of all anomalies to 15.5% of all anomalies. So that's an alert. This is an image from our Slack channel. That's an alert that the system sent us to say, look, there's something weird with the algorithms because we're seeing so many more high confidence anomalies that warrants taking a look at it. So when I go into the system, I also look at the full distribution to see how everything changed, and you can see the bucket of that classifier that gave it the highest score out of 10. Actually changed its distribution on around June. It started June 9, 10, became very significant, and continues like that. So when I went to investigate it, I go into the system, and this is a screenshot from our system showing me, oh, this is the metric that had this anomaly. And just prior to it, I see that for one customer, there was an event that was correlated with this change. There was a configuration change event for one particular customer that was correlated with this anomaly. And when talking to our customer success, we realized they did some sort of configuration change for the customer, the way the data is being sent, that caused a lot of high significance anomalies for that customer to occur. And actually, because that is a big customer, it affected the overall distribution of all the models brought together. So we went back, changed that configuration, and now everything's back to normal. So this is we would have never been able to pick this up ourselves because we are a small team. We cannot sit in front of dashboards all day long. And we would have heard about it at some point from the customer saying, well, how come all of my anomalies are such a high score? But this way we avoided it and fixed it even before anybody noticed it. So with this, I conclude the talk with this example. I wanted to summarize it with one sentence. Monitoring of your machine learning in production is critical. If you add automated anomaly detection to it, you actually have a very scalable machine learning monitoring capability that lets your team not worry about what's happening in production and just worry when you get an alert. And especially as you deploy more and more things into more and more models and instances of models into production, this becomes a very critical capability if you don't want to get bitten like all the examples I showed before. So you're free to download this ML Watcher package or use something that you want. And if you use this package, basically you can create your metrics and save it and visualize it anywhere you want, so you don't have to be an Anodot customer for it. But of course, if you want also anomaly detection on top of that from us, feel free to contact me at this email, and I'll be happy to take any questions right now.
Yeah, thanks a lot, Ira. So there's a few questions in the board, and I'll kind of leave it to you to look through the chat and answer those. But if anyone else has any questions about ML monitoring, feel free to post those in the chat. Prefix it with the Q:, and I'll let you take it from here, Ira. Thanks a lot.
Yeah, no problem. All right, so there's a question, yikes. Thank you. Is the tool open source? So what I mentioned, this ML Watcher, is on GitHub. So this is basically Python code that we wrote that can once you wrap it around your classifier model, the output of it and the input, you get the output and input distribution of the features, and it gets collected. It can be collected locally and then put in any visualization tool. If you want the anomaly detection, then either use an anomaly detection that you find on those metrics, or of course, if you want, you can contact us and use ours. And yeah, the link for the tool, it's right here in the presentation. So hopefully you can copy it. I'll share it in the chat afterwards, so you can just click on it. There was a question if I can explain what is the input feature distribution plot showing. The x-axis is time, the y-axis, what is it? Is it a single point per sample? Okay, so let me go back to my presentation and talk about that. I'm assuming we're talking about this, or maybe, no, this is not the input feature distribution. This is the input feature distribution. So what we're seeing here, let me try to make it a little bit bigger. So the x-axis is the as you said, the time. The y-axis is actually a stacked view of the, I believe this one is the average pixel intensity for all the images that flowed within that time bucket. So this was measuring every, this was creating a data point every 5 minutes. We were basically pushing images, around 100 images per 5 minutes for the classifier to classify. And then from those 100 images, every pixel location, we generated what is the mean of it. We also generated a standard deviation, IQR, and other features, but this plot is showing the average of it. And basically here, it's showing for some of the pixel locations but there was a significant change out of the 28 by 28 features in this case, because every pixel here was a feature. I hope that answered the question. Oh, thank you. Somebody put the link for the tool. Thank you. How does this compare to AWS SageMaker model monitoring? First of all, it doesn't have to be in SageMaker or AWS. The ML Watcher is basically code you could put anywhere, and you could use it at any location, on whether cloud or not. So in terms of creating the data for what you're monitoring, the open source is for you to use anywhere. In terms of the anomaly detection and the actual monitoring using anomaly detection, as far as I know, AWS SageMaker did not implement that yet. So what I know about our system is that you can feed it hundreds of millions of these time series, and you would still get very accurate anomaly detection on all of this data, no matter how it looks like. This is what our customers use it for. Most of our customers don't use it for monitoring machine learning in production. I have to say that they're using it to monitor a variety of things, from revenues to number of users and things of that nature. And our system is very scalable for that. So you're free to if you want to try both, I'll be happy to do that. No, not just sklearn models. Our ML Watcher works, the open source ML Watcher works in Python, so anything in Python, you can wrap it in Python. You can, even if it's written in Java, as long as you can somehow get the output and inputs into Python, you can use it. In terms of the anomaly detection, our system, it can read any telemetry data from any source. So it doesn't matter. Is the anomaly detection part of the? No, it's not part of the repository. So this is what we do as a company. So we actually provide it as a SaaS service, and I don't want to talk too much about Anodot. This is not a self-promoting talk for the company. But feel free to go to our website and see exactly what we're doing and how we're doing it, and send me any questions in particular if you have about it. I'll be happy to answer. I don't want to go into self-promotion here for my company. What type of businesses we're working with? Well, okay, the question's forcing me to do that. That's fine. We work with so some of our customers are gaming companies like King and quite a lot of others, mobile gaming, telcos from Comcast, Deutsche Telekom, AT&T, and others, and also online services. So basically, our system is designed to provide anomalies in real time on millions of telemetry data, and there are a lot of different use cases that it fits. What we've noticed is that the best businesses that have the most leverage from our systems are ones that are very data savvy and really require continuous monitoring and almost real-time monitoring of things that are happening in the business. The next question: what does traditional DevOps mean to model monitoring? So I think as time progresses, we'll see DevOps be involved more and more in model monitoring. I think it's because this is a relatively new area of the DevOps are not used to seeing a lot of machine learning in production unless you're in a company like Google, Facebook, and that does a lot of machine learning, that has been doing it for a long while already. Most DevOps are very good at monitoring the performance of the model or of the software, meaning its latency, error rates, things of that sort, saying that they are actually functioning right now, but they're not, or monitoring the network, monitoring that the servers are running and things are being deployed correctly, but actually monitoring the functionality of the model itself, whether it's doing the right thing, that's tougher for DevOps today. I mean, I don't think the most DevOps really understand it yet. Even a lot of data science teams don't fully understand the complication of that yet. Until you go and deploy some of these models to production and see them fail and see their failures, it's kind of you get bitten once or twice and you don't really understand what you need. And so I think it will take time, but eventually this will be under the responsibility of DevOps or MLOps. And I can tell you that within my team, first of all of my team, we all monitor these alerts for our production environment, and we decided together what we need to monitor to make sure our algorithms are running properly in production. But we do have a function of an MLOps person in the team that is in charge not just on the infrastructure and the pipelines of the machine learning, but also this is part of what they think about. And that's important, and I think this will be more and more prevalent in a lot more data science team. Can the tool do monitoring in real time? Yes, real time up to 1 minute, at least our tool. So 1 minute, up to 1 minute granularity. The ML Watcher, you can actually set whatever time buckets you want for it to collect data. You can set it to bucket it at 1 minute intervals, hourly intervals, 30-second interval. So you can create whatever interval. So if you're running a lot of ad bidding algorithms, maybe you need the interval to be very short. And if you're doing something that classifies an example once a minute, maybe you want to wait for an hour, aggregate all those examples, and then get it. All right. So question. What are your thoughts around statistical operations that can be applied to compare between data input and output distributions? So I'm trying to think whether it makes sense to take the input features and output. I would have to think about it, whether there are operations that we should apply. I haven't thought about that, so I don't have a good answer right now. I would be happy to take it offline and talk a little bit more about it to gauge this thought. Okay. What was the driving force behind building ML Watcher at Anodot? Was it solving an internal use case you had? Okay, so actually no. Our driving force was so we've been monitoring our models in production from practically day one, even from our alpha. Well, I would say from our beta version, when we got bit a few times and realized it's not just about the performance, but we really have to take a look at the output and the outcomes of these algorithms to make sure that nothing is going wrong. So we actually first built it as a customized thing. So we actually built it into our code, getting out all the data, really very deeply into that code. And then we've been meeting with other data science teams talking about this same type of problems and realized that other people are facing similar problems. And we knew that we had a way that can help, at least with the scalability aspect of it. But we also saw that a lot of groups struggle in the first place is to actually get the metrics, collect the metrics, understand what metrics to collect. So we decided to take like a small project to write this open source and see what is, and so we can provide it to others. So they can do it. I really believe that without monitoring of these models in production, and at this point in time, in most companies, I believe it should be the data science team that designed the algorithms that needs to monitor them. because most others will not understand what they need to look for. So anything out there that helps with that is something that the community needs. And whether you push it to an anomaly detection afterwards or put it in your dashboards, anything that you do to track it is really critical, and would actually accelerate the trust in AI and machine learning throughout the company that you're working for, or throughout the industry in general. Because those glitches, when they happen, they cause a lot of mistrust. Just think about autonomous cars. I mean, people make accidents all the time. One accident with an autonomous car makes the headlines. So the same thing within a company. When these glitches happen and they end up costing the company $300,000 or $10 million or any amount or trust of their of the customers, then there is a tendency, because this is so new, for executives to mistrust the whole field, and it slows things down. So it is in our best interest to make sure that things are working and functioning properly in production, because when they don't, it slows everything down for everybody. All right. Do you also look at the pen layer feature output? Okay. So in this case, we did not. I think that if you're looking at particular models, so when we build this ML Watcher, we wanted to build it as simple as possible, as generic as possible, and irrespective of the internal model that actually does the prediction, whether it's a deep learning algorithm or a different algorithm like XGBoost or whatever it is. And so we only looked at the input output. I think that if you're looking at if you know that you're using particular models, you probably also can put in hooks inside the model to extract some features from there. But at the very least, this is kind of the least common, the most common denominator: input feature distribution, output prediction. And anything you add in the middle is only a benefit, but at least that should be it. And in some cases, you might even want to go further down the stack of your feature generation technique, whatever that is. The pipeline that generates your feature, you probably want to put hooks in there and monitor that as well. But these are kind of the two basic ones that if you have them, at least you're covered somewhat. To know that, that your pipeline generating the features had something wrong with it, or the outcome had something wrong with it. All right, so if there are no further questions, I'll be happy to take questions via my email or any type of method you want to connect to me. And thank you for attending this talk. It was a real pleasure and real easy too. And now I can finish my cup of coffee, and I hope you all have a great cup of coffee too. Thank you.